This is the 11th video supplement for CIS 351, Grand Valley State University's course on computer organization and assembly language. In this video, we'll learn how to build an adder. So after 10 videos of basics like gates, binary, truth tables, big hammers, and such, it's time to actually build something useful. We're going to start with the adder, which is in many respects the central part of a CPU. An adder is a circuit that takes two integers as input and returns their sum. There's a fixed upper bound on the size of the integers that a typical adder can handle. The numbers here show this size. For example, this adder can only accept integers in the range of 0 to 255. This notation, that slash through the line with the number near it, indicates that the wire is really a bundle of 8 wires. Although inputs A and B are conceptually single inputs, each bit of that 8-bit input needs to be physically carried on a separate wire. Think of a bundle kind of like an Ethernet cable. You carry it around and work with it as a single unit, but inside there are really 8 separate wires that each carry an independent signal. As you can see, using bundles instead of separate wires tends to make the diagram less cluttered and easier to follow. If you look closely at the output, you'll see a potential problem. Adding two 8-bit numbers sometimes produces a 9-bit result. For example, 255 plus 255 is equal to 510, and 510 requires 9 bits. To handle this, adders have a 1-bit output called the carry out. The least significant 8 bits of the sum go on the sum output, and the most significant bit goes on the carry out. Now yeah, we could simply make the output 9 bits, but doing so would complicate other parts of the CPU design, and we'll see why in a future video. Also, later in this video, we'll see an example of how it's helpful to have that carryout separate from the sum. Alright, so now the question is, how do we implement an adder? We saw in video 6 that simply implementing the sum of products based on the truth table is not practical. It doesn't scale. And therefore it's effectively impossible to use this brute force technique to build the 64-bit adders found in most desktops and laptops today. So we need something more clever. Now what does it mean to be more clever? Does that mean we just need to sit around and think really hard until the light bulb in our head happens to go off? Well, I suppose we could do that, but we can be more intentional than that. In fact, we can take some inspiration from programming. There's both an art and a science to writing computer programs. The art of programming refers to the fact that there isn't a set algorithm you can follow to write a program. Programming requires a certain amount of cleverness and inspiration, but it's not all art because there are general principles you can follow to point you in the right direction. Designing hardware has a similar balance of art and science. There isn't a single algorithm you can follow that always gives you a practical solution. Unlike programming, we do have an algorithm. We saw that in the first video, but as we've also seen, it doesn't scale, so we can't always use it. Just as with computer programming, there are patterns you can follow when designing hardware that will get you close to a really good solution. For example, when one of my beginning programming students gets stuck, I often suggest that we work through the problem first using pencil and paper, or maybe a whiteboard. And then we can look carefully at the individual steps we use to arrive at that solution. And although the problem may seem overwhelming when you look at the entire problem at once, the individual steps tend to feel much more manageable. So let's see how that approach helps us build an adder. Here we have 473 plus 156. So how do we solve this problem with pencil and paper? Well, you take it one column at a time working from the right. So we start with the ones column, 3 plus 6 equals 9. So we write that down and move on to the tens column. 7 plus 5 is 12. We write down the value in the ones place, the 2, and we carry the 1, and then 1 plus 4 plus 1 is 6. We do one more just to point something out. So here we have 473 plus 856. So this time, 3 plus 6 is 9, 7 plus 5 is 12, write down the 2, carry the 1. Now we have 1 plus 4 plus 8, which is 13. And notice here that even though we added two 3-digit numbers, we got a 4-digit answer. Just pointing that out as it ties into the idea of the carry out that we'll see in a minute. So this is the algorithm that many of you learned in elementary school. It turns out that this algorithm works for numbers in any base, including binary. So pause the video and add these two numbers. All right, so just like if this was a base 10 number, 0 plus 1 is 1, so we write down the 1. 1 plus 1 in binary is 1, 0, so we write down the 0, carry the 1. 1 plus 0 is 1, 1 plus 0 is 1, and so we get an answer of 1101. All right, and just one more example again. Starting from the right, 0 plus 1 is 1, 1 plus 1 is 1, 0, write down the 0, carry the 1. 1 plus 1 is 1, 0, write down the 0, carry the 1. And again, here we have 1 plus 1 is 1, 0, and so we started with a 4-bit number and got a 5-bit answer. So that last bit is our carry out. Now if you look back to the right, let me just point out that there's also a carry out there, but that carry out is the implied leading 0. So now, instead of trying to dive in and build a complete adder at once, let's build hardware for each of the individual steps. So the first step was to add the 2 least significant bits, the ones on the right. The 2 input values for this subcircuit come from inputs that we'll call A0 and B0, the least significant bits in that 8-bit bundle. And then the output gets put on S0, the least significant bit in the 8-bit sum bundle. Now when we're focusing on just this small piece right here, we have a subcircuit with only 2 inputs and 2 outputs. This piece here with just 2 inputs is small enough that we can attack it with that brute force big hammer. So we'll start with a truth table and pause the video and fill this truth table out. All right, one way to look at this is to treat C0 and sum 0 together as a single 2-bit number, which just counts up the number of 1s on the input. So with the first row, we have 0 and 0, so there are 0 1s, so we put 0, 0 on the carry out and the sum. The next 2 rows have a single 1, so we put 0, 1 on the output. And then the bottom row, of course, has 2 1s, so the output is 2 or 1, 0. Now, how do we implement this truth table? Remember, when you have a truth table with more than one output, you can just treat each output bit separately. So if you look at the C0 output, you'll notice that it is simply the truth table for an AND gate. Similarly, if you look at the sum column, you'll see that it is the truth table for an XOR gate. So this small piece of an adder is implemented like this. And we call this subcircuit that adds 2 bits a half adder. The next step, of course, is to handle the next column to the left. This time, the input is coming from bundle bits A1 and B1. The output goes to S1. But this time, the circuit has 3 inputs. The 2 external inputs A and B, as well as the carry from the previous column. Now again, with only 3 bits, we can attack this using a brute force approach. So here's the truth table. Again, pause the video and fill out this truth table. Once again, the approach is just to treat cout and sum as a 2-bit number that's counting the number of 1s on the input. Once again, the top row has 0 1s in the input, so the output is 0, 0. Rows 2, 3, and 5 have a single 1 among all the inputs, so their output is 0, 1, and so on. So pause the video again and design a circuit that implements this truth table. Here is just one of many possible solutions. Now this circuit that adds 2 bits and accounts for a possible carry in is called a full adder. I guess if you're not dealing with a carry, you're only doing half the job. Now once we have this full adder, we can repeat the full adder process for each of the remaining input bits. And when we do that, we end up with what's called a RippleCarry adder. So notice the yellow lines in the diagram. This adder is called a RippleCarry adder because the carry ripples through the adder from left to right on those yellow lines. Now remember, this is an 8-bit adder, which means it can only handle inputs between 0 and 255. But if you want to be able to add bigger numbers, you can just continue this pattern and make a longer chain of full adders. Be aware that if you look up the implementation of a RippleCarry adder in like a textbook or a web page, you will typically see something more like this, where the full adders are just labeled boxes and don't show you the details of how that full adder is implemented. If that seems strange at first, stop and think about source code. In particular, method calls. Consider this source code for a selection sort. You'll notice that this code calls two helper methods, location of minimum and swap. In making those method calls, you only see the names of the methods. You don't see how they're implemented. And in most cases, that's a good thing because it's typically easier to follow and understand how this selection sort code works when we've abstracted away the specific details of these helper methods. So compare what you're looking at here to a longer implementation where we spelled out all of the details of location of minimum and swap. Most people find it a little more challenging to figure out what's going on here than in the version where the details are abstracted away. Likewise, most people, especially once they're used to working with hardware, find it easier to follow and understand a circuit when it's shown like this with the abstractions rather than when it's shown like this with all of the details of all the sub-circuits cluttering up the diagram. Right, now one last minor adjustment. Most RippleCarry adders actually look like this, where there's a full adder handling those rightmost bits instead of a half adder. And then we also have that carry into that rightmost full adder being an external input. Having this carry in is useful because then we can chain smaller adders together to make larger adders. So in this case, we've chained together two 8-bit adders to make a single 16-bit adder. Notice that when I draw this out, the 16-bit inputs are then split into two 8-bit inputs, where half the bits go to the lower adder and half the bits go to the higher adder. So that was the promised example of how a separate carry out bit can be helpful. We'll also see some other uses in future videos. And so to summarize, now that you've watched the video, you should be able to perform binary addition by hand, and you should also be able to sketch all of the parts of the RippleCarry adder that we went through in this video, a half adder, a full adder, and even the full RippleCarry adder. And not only should you be able to sketch it, but you should also be able to explain how it works. And then finally, also be able to show how you can chain those adders together and explain why that chaining works. All right, so over the next few videos, we'll discuss how to measure the time and the speed of circuits in general. And then we'll use those skills to analyze the size and the speed of the RippleCarry adder and look for possible improvements.